Welcome to the next lecture in quantitative methods in chemistry. We are into the 6th week where we have started to understand what is data, what is error, what is the uncertainty associated with them, how to fit data and concepts of that sort. As we are moving forward to this week, we will be trying to learn how to use different software in order to document your data and perform even the analysis within this software. The reason why we would like to do this is because as science has become enormous, one starts to acquire quite an amount of data before they start writing their observations. So rather performing inferences on their observations. So it does help to have all the data put within a given concise format such that it can be easily transported across, and at the same time one is able to analyze the data anywhere, everywhere at the disposal of a computer. So in order to do the same, we will be taking an example like we had done in one of the earlier lectures, where we will be taking an example of how a burette can be calibrated. And as always, we should be also taking a look at the different steps that are required in order to do such an experiment. While doing so, we will also be taking a look at where all systematic errors could come up and how this data can be looked upon to see whether you have systematic errors that has cropped up, in order for you to repeat the experiments if possible. So in order to do that, the first thing would be to understand the aim, where the aim of this experiment is to calibrate the given burette. As we all use a burette in many different experiments, this I hope will be able to make connect with the students who are listening to this lecture. And we will try to analyze what is the accuracy and precision for that given burette. As you might remember, we defined accuracy is the agreement between the sample mean that you have gotten with the true value, and precision is how far do these measurements deviate from the sample mean. If you are able to do infinite measurements, meaning that if you are able to have a lot of measurements which samples the entire population, then you go close to the population mean, and the standard deviation will be the standard deviation of the population itself. As always, we try to start by asking what are the materials required. As we started by trying to say we are going to be calibrating a burette, we need the burette, and in this case we are taking a 50 ml burette. And as you might remember, all burettes have a certain listing at a given temperature. So this is a burette, let us say we take it at room temperature where it is listed to have the minimum error that comes up. We would also need a conical flask, which we would end up collecting the liquid that we aliquot out of the burette. Conical flask is better than a beaker because even if water starts to splash, it does not end up leaving the flask. If in case of a beaker, you could have where a droplet goes out, that results in systematic error that could come up. So therefore, most often for any titrations, we end up using conical flasks for this reason. And of course, we also would like to stopper the conical flask, where you would realize if you are making other measurements, no contaminations end up coming up in such a flask. Thermometer, as always, so as to remember or at least make a note of the temperature at which you are making a measurement. In addition, for this experiment, this is also going to play a role, and one could end up using a mercury thermometer or an ethanol thermometer. If you are doing it at room temperature, ethanol would be safer because in case the thermometer breaks, there are no issues. Of course, if you are doing experiments at a much higher temperature, let us say at 80 degrees Celsius, then ethanol thermometer will not work, then you might have to use a mercury thermometer. You are able to realize that depending upon the setup that you are going to end up having, the apparatus also could slightly change, and a judicious choice of the same has to be done while you are about to set up the experiment. Last but not the least, one of the important equipment that one might end up needing in this is the analytical balance, which would help us determine the amount of aliquots that we end up adding. So now let us foray into the experimental procedure. It is a relatively simple procedure. The first step is to measure room temperature with a thermometer. This is required because you are going to be having water in your burette, and this water is going to be aliquoted out into the conical flask. If you add a known amount of water, and if you are able to measure how much you have added, this would help you understand how much is the accuracy that comes out of the burette. Remember, it just not as the accuracy of the burette, it also depends upon how you end up aliquoting. If you start making a few mistakes here, let us say you have a certain systematic error that comes up, this is going to end up not just as a calibration of burette, it is also ending up calibrating your own standards of how much you end up adding. Okay, the next step would be to weigh mass of the dry conical flask. This is done because using this flask is where you are going to be adding different volumes of water to measure how much comes out. So, this helps you understand if you are aliquoting a certain volume V from the burette, and if you are able to measure the same volume by getting the mass and taking a product of the mass with density, you will be able to agree that you are doing whatever you are anticipating to be doing. Okay. Before you start the experiment, rinse the burette with the distilled water that you are using. Remember, the emphasis on distilled water is made here. This is to ensure that the density that is measured at range of temperatures for this water is very well known. If you are using tap water at different locations, it might have different salts which might end up changing the density of water. Therefore, our estimates could be wrong and result in systematic error due to the water that you end up using. So, it is always a good idea to be using distilled water for this experiment so as to accurately determine the calibration of the burette and the procedure. Remember to fill the burette up to the 0 level. This is a mistake many students end up doing, where they do not fill up the bottom part of the burette where the solution comes from, and this results in a systematic error of about 1 to 2 ml depending upon the make of the burette. Yeah, that is the same point that is written here. So, generally protocol, as you are able to realize, will also have the information of do's and don'ts in order to minimize an influence of the error that might end up coming. Okay. Now starts the experiment. You carefully aliquot 2 ml of the distilled water from the burette to the conical flask. After having done that, close the conical flask and then weigh it again on the weighing balance. Since you have weighed the empty conical flask and now you are weighing it with 2 ml addition, you will be able to understand how much of mass of water you have added. Using the density, you will be able to convert the mass into volume and determine how much volume you expected to add and how much volume you ended up adding, therefore helping you how to calibrate the burette. So, repeat this task by adding 2 ml of water again and again until you have certain number of measurements, so that you can understand whether you are able to repeatedly add carefully, or if there are any mistakes that end up coming. If you might remember, the constant error or proportional error could be determined from the experiment that you are doing. We will now take a look at an animation of the same so as to understand what is that we are trying to do. Let us assume that you are trying to make a measurement such that you are going to determine how good the accuracy and precision is. As you might have remembered earlier, we will be taking an example of arrows hitting a dartboard, and let us say you want to hit right at the center of the dartboard. How are you going to achieve this? And in order to do this, all the dots, if you might remember, were represented in a 2D surface, as you might end up seeing here, coming up as dots in the measurement. And the average and the standard deviation, which help us understand accuracy, would be given as a dot that goes in the center with bars that help you understand what is the standard deviation that end up coming. And let us say these are the 4 different measurements that we end up having. We had already seen this during the lecture, which gives you better accuracy and which gives you better precision. As a scientist, if you are calibrating the burette, you want to ensure that if you are adding 2 ml, you exactly want to add only 2 ml and not more or less. As you are able to realize, these are 4 different scatters one ends up having, just to exemplify the point that we are trying to understand, who gives you better precision, who gives you better accuracy, and who neither gives you accuracy or precision. So, let us say xi is the observed value, meaning that you are trying to make measurements, and x is the true value, capital X is the true value, meaning that that is where you want to be as close as possible after your measurement, and x bar is the mean value which is trying to pick up what is the true value. Then what we end up doing is that these are all the measured or the observed values. You determine what is the mean that comes out of this measurement and take a difference between this mean to that of every observed value, so that you have an understanding of how much residuals come into place, meaning that how far is each measurement from the sample mean itself. Having done that, the next part would be to determine how the sample mean and the standard deviation parameter would help you assess accuracy and precision. So, you want to ensure that you have a certain number of measurements n that goes through, and sigma as a sample standard deviation as given here. In this case, it is a population standard deviation, assuming you have good number of measurements, and in the case that n is small, this ends up being given as the square root of sums of squares between difference between the sample mean and the observed value divided by n minus 1 for n number of measurements where n is a small number. Now, having done that, let's try to look at how can we distinguish the dartboards that we saw a little while back. What you end up seeing is that if you want to hit the middle of the dartboard, the average nicely comes up to the middle, the standard deviation is fairly within the first circle. On the other hand, in the second case, what ends up happening is that although the average comes up nicely at the center, the spread of the points are quite a bit. And you are able to realize some of the points are even falling beyond the 3 standard deviation, which does make sense because you are looking at 0.3% of the values which might end up falling out. And on the other hand, in this case, what you are able to realize, while the true value is at the center, the average value for all of this, which is the sample mean, comes up quite far away, although you have very good precision that ends up coming up. So this is one of the cases where one has to be careful. Although you have poor accuracy, you have very high precision, and not always or never in any given scenario this is a good reason, because this ends up resulting in a biased analysis. Now, going to the next case, if you see the true value that is here, the average value for these measurements are far away and the spread is bad, which results in an imprecise and an inaccurate measurement. This is a very bad scenario to be existing or working in. Okay, so now let's take a quick look at how this experiment will be performed. You're looking at a burette here where the distilled water that you end up adding is carefully added onto the burette. Ensure that the burette is opened so as to fill the bottom portion of it, which will ensure that no systematic errors come into place. If you are not filling this part, you are definitely going to introduce a certain constant error across each of your measurement. Now, having done that, we are trying to give a schematic where, okay, you measure the weight of a stopwort conical flask, and once you have gotten that, the next step would be to take the conical flask and carefully add a few ml of water into it and repeat the measurement in the weighing balance. The difference in this would help you understand how much mass of water has been added. And then this is where we are coming into this week's topic of how the data can be entered into a software. If you are able to realize, a good scientist would end up making a table that's comprehensive. As you are able to realize, these are the measurements that are being done, and these are the different volumes we end up adding. In this case, we are trying to say, let's say you do 25 experiments where n equal to 22, by adding 2 ml, you are expected to finally finish off in 50 ml. So the next step while you are doing this would be measuring the mass of the conical flask with water, which means that you should have also had the empty weight of the conical. Remember, the density of water is going to play a role, because as a function of temperature, density also changes. So it's a good idea to have the temperature to start with. Now that once you measure the empty weight, after as you keep adding the aliquots, you will be able to measure what weight has come through, and therefore you can determine what mass is added and what is the actual volume difference that comes up. Having done that, you will be able to find the differences for each of the aliquot and get the mean from the distance, the difference of the mean from actually every addition will give you the residual, from which we will be calculating the standard deviation. Of course, first step would be to get the differences from each of the measurement to the mean as given in the residual, square of the residual, sum of the squares of the residuals, then use the formula for the standard deviation, and finally get the sample standard deviation in terms of sigma. So once you get this, you can actually plot as a function of volume that you ended up adding in the burette, what is the actual volume that came up, which will help you fit and determine whether your accuracy is good, which we will be seeing in a moment, and how off are you from each of the measurement that ended up happening. So now let's start to go ahead and pick up some of the skills that you might end up needing for the software analysis. Okay, so now we are moving on to how this experiment can be nicely documented with the use of a software. So here, as you are able to see, this experiment is done at 300 Kelvin, so as to get the density of water. If you realize, the density of water at 300 Kelvin is 0.9965, which we end up writing here. Many of the software, spreadsheet software in particular, end up having their own bias on how many decimal points to indicate. So it's always a good idea for you to go and carefully change whatever number of significant figures make sense. And let's assume that for this measurement, the scientist measures a total mass of 60.253 grams, where the uncertainty exists the third, the last decimal, basically in 1 milligram for each of this measurement. And let us say that the following measurements were made. Oops. Let us say that after the scientist has carefully determined the empty weight of the conical, he ends up adding 2 ml aliquots each time to perform 12 such experiments. Here the case n is equal to 12, and he is also able to measure the mass of the conical as a function of this volume that has been added. As you are able to realize, this comes up with the mass of the conical. So the first step that would end up happening here is to take the difference in each of the steps so as to understand how much volume has been added. So we have been looking at how spreadsheets could be used for different analysis. We are going to be ending up doing the same thing, where we carefully add formulae in order to get whatever we want. So in this case, you want to understand what is the mass of the 2 ml aliquot addition to that of the mass of the conical itself. So this is going to be in the cell C4, as in most of the spreadsheets. You are going to have alphabetical sorting up the top and numerical sorting on the left. So a given cell can be attributed to a certain alphabet and a number. In this case, you want to take the difference between the mass of the conical, which is entered in the cell C4, to that of the mass of the empty conical, which is in H1. So what ends up happening here is that you write the formula C4 minus H1. So if you are able to realize, the C4 is highlighted with a blue while the H1 is highlighted with a red, which helps you understand which two parameters are you taking a difference between in this measurement. Once you hit enter, you are able to realize that this has carefully calculated the difference between this value and that of the empty conical flask. Of course, one can repeat the same process by typing it, where you take the difference between C5 and that of H1, and so on. Although this appears a little automated, this is indeed a boring and a laborious process, and there are better ways of writing such a formula, where you actually say it's C4 minus $H$1, which indicates that if I am copy pasting this set of formula onto these cells, what ends up happening is that you will carefully notice is that as you copy paste, C4 becomes C5 while the H1 does not change. So this helps you, because if you are having many different values, it takes a lot of time for you to take the difference carefully with this. Otherwise, if you copy paste this formula, this will be erroneous without the dollar, because it will end up taking differences not from this but also from the other cells that go here. Okay, so for instance, why don't we take an example of what happens if we do not have the dollar here. Well, the first value will come up fine, the remaining values will not make sense. As you are able to realize, it is not able to understand the value here because it is trying to take the difference between 64.2301 to that of the square of the residual, so which does not make sense, it is a string. And as you go forward, you are able to realize that this value is the difference between C7 and H4, which is not the difference that you want to end up taking. So one has to be very careful where you include this dollar, such that for every value you end up measuring, the dollar one does not move at all. So this helps you understand how to use spreadsheets in order to make differences across different cells, and keeping one cell constant while the other cell increments based on the value that you want to measure. So now that you know what is the mass of water that has been aliquoted, one has to remember to get the volume, because you are adding volume and you would like to see what is the response that comes from a given volume. So the volume is going to be given by the product of mass to its density. Once again, in this case, I am using another formula that goes as D4 asterisk E1. The asterisk is a symbol for multiplication that we end up using in all these software, and division is plainly given by a backslash. So here one is able to realize that D4 star E1 is what you want, and similar to the previous example, if you copy paste this for all of these cells, it is going to end up having a problem, because while you want to increment the D you do not want to increment E because it is a single value. So, what you end up doing is to give it as a $E $1 in the formula. Now, if you copy paste, it would make total sense, where carefully the volume that has been added in each of the aliquot nicely comes up. Now, what you are able to realize is that for every 2 ml increment, you are able to see the amount of volume that you have added. So, the first step here would be to take the difference between how much you have added to that of how much you expected yourself to add. So, what you end up getting in this row, this can be happily copy pasted, largely because all these formula end up going as a serial increment. So, we can also copy paste this. So, now what you see is that for 12 different measurements, you have been fairly accurate enough where the mistakes happen in most of the cases in the second decimal. If you carefully pay attention, for these measurements, the mistake happens in the first decimal itself. This helps you understand the fact that there are measurements where one ends up adding a little more or a little less. One way of determining where do you fall is to take the average of these differences that end up coming by having the average formula. So, this is once again where software help, where the average is nothing but the ratio of the sum of each of this value to the total number of measurements. In this case, you would end up summing all of them in F, dividing by the total number, which is 12. So, but instead of doing that, you end up getting the average in a single shot. You are able to realize the average nicely represents values across, meaning that you have some values that deviate by minus 0.19 ml, while others that end up deviating with minus 0.10. So, the average of all of this, including values that go away and in some cases positive deviations, to finally come up at an average of minus 0.05. So, this once again indicates that you are probably erroneous in the second decimal, but thinking about the 3 standard deviations that come, you are probably looking at minus 0.15 also exist in a value, which nicely does happen in this data that you are trying to look at. Now that you have gotten the average of all of these measurements, the next step that you would like to do is to take the difference between the sample mean and that of each measurement. Once again, if you realize, you want to make sure the sample mean is kept constant. So, you want to make it as $F $16, and you start making the differences, and what we end up getting is that these are the residuals for each of the measurement that you end up making. So, just before going ahead, let us see whether how good has our aliquots been. So, I am trying to plot the aliquots that you ended up adding, in this case the column B with that of column G, carefully selecting only the values that we would like to plot. So, if you go to insert and plot a scatter plot, what you are able to realize is that in the x-axis you have the different values, rather the volumes that you aliquoted, and in the y-axis the residual, meaning that how far from the average that you deviated, and you are nicely able to see good amount of points less than the average and more than the average. Of course, in this measurement, it's quite interesting to see that the initial first values are less than the average and the final values are above than the average. This could also indicate a bias or a systematic error that comes up, but for now let us not worry about it. Let us go ahead and try to understand what is the standard deviation. In order to do that, we would like to take the square of it, which is given by that cell caret 2. Caret indicates to the power of, and 2 indicates it's a square. If you want to take the cube, you would do caret 3. So, now you end up getting the square of the residuals, because if you remember, standard deviation is nothing but the square root of sum of squares of the residuals to the total number of measurement, or total number of measurements minus 1. In this case, since you have only 12 measurements, you have to do square root divided by n minus 1. So, what are we going to get here? Let us try to take the sum of all the residuals. And you can also try to get the average of the residual. You see in this case the average of the residual nicely falls very close to 0. This indicates that almost every measurement from the average measurement that you end up getting, you nicely have equal number of points above the average and below the average, and the magnitude of this value being small indicates that you do not have large errors that have come up. Okay, now that you have taken a sum, you want to get the following measurement, which is going to be this value divided by total number of counts that you end up having. Luckily this kind of software nicely have the kind of count that you end up having, meaning that it can itself count how many values you have. So in this case the count is going to be obtained by using the formula or the library function called count and selecting the values that you have gotten it, and since it is n minus 1, I am taking h17, which is the sum of the residual square divided by the count minus 1. So what you end up getting is this is the variance, and the standard deviation is going to be the square root of this variance. Okay, so now that we have understood this is a representation of the precision of measurement, what is my average? We should be able to understand what is the average that comes up by having yet another cell that we can define here. The average can, on the other hand, can also be obtained by a quick fit. I hope you have learnt what is fit in the previous classes. So let us try to do a fit of the variable that you ended up changing, that is the independent variable, to that of the dependent variable that you ended up getting from the measurement. And if you do a scatter plot, you will nicely get a linear curve, and this should be helping us to understand what is the accuracy that comes up. Let us try to add a trend line. Trend line helps you get a fit. Nowadays software helps you get all this in a single click, and you are able to remember that for these kind of measurements, if you added no volume of water, you are supposed to get no volume of water. So therefore you can set the intercept to 0, meaning that when you have added no volume of water, you expect no mass of water to be obtained. You can also display the equation on the chart. To start with, let us also see what happens when you do not have the intercept set to 0, and you can also have a reasonable way of determining what is indeed the fit, whether the fit is good enough or not. Basically the linear regression fits help you get a parameter called r square. In this case the r square is very close to 1. You might remember r square of 0 means it is a poor fit, and r square of 1 means it is an excellent fit. And what you are able to see here, while x is the variable that you are varying, this is the slope that you end up getting, this is the intercept that you end up getting. The intercept says what is the constant offset that you end up getting, while the slope gives you an indication of how much proportionality comes into play. Let us say that you wanted to add 2 ml every time and you precisely and accurately added only 2 ml, this curve is going to be fit with an equation which is y equal to x, meaning that for every 2 ml that you added, you are able to measure 2 ml correctly. But you are able to realize there are deviations that come up largely because there have been differences that have come due to various different things. Of course, due to systematic errors that could come from the weighing or from the aliquots that you ended up doing where you added 1 drop more or less. On the other hand, maybe your temperature was fluctuating during these measurements, which once again ends up having errors that might increase if the temperature kept on changing, fluctuating during these measurements. And the standard offset could have come from the basic fact that the burette or the weighing balance was miscalibrated, meaning that which is why before starting any experiment, calibrating the instrument becomes important. And of course, the fit makes you happy in this case because the fit seems to be quite reasonable, where all the points are in fact contained within the fitted line, which is shown as dotted line in this case. So you are able to see that the dotted line nicely passes over each of the fitted value or each of the measured value, which indicates that you have gotten a reasonable fit. Okay, now having understood that, why don't we try to see what is the average value that had come up for each of this measurement. In order to get that, what we will end up doing right now is to take the difference between the values that you have obtained. So for the first one you already got 2 ml. For the next aliquot of measurements, we can try to ask what is the difference between my subsequent measurements, and then you copy paste this carefully to understand what you end up getting. So now what you are able to realize is that for every 2 ml that you try to add, you are having subtle deviations that come up, meaning that in this case you ended up adding 10 microliters more, in this case you ended up adding about 40 microliters less, in this case about 50 microliters more, and so on. Here about 100 sorry, not microliters, about 10 about 10 microliters more, okay, I think, and then about 100 microliters more here. So let's try to take the average that comes up here, and then the average will help you understand how accurate you were. You wanted to add 2 ml and you are actually at 2 ml, and you should be able to even get the standard deviation of this measurement. Let's try to see how different it's from the standard deviation that you have measured. If you are able to see, the fitted value gives 0.0529, and that's somewhere close to what you are getting here. So you are able to realize the same analysis could be done in subtly different ways, which give you subtly different values, but overall what you are able to understand here, you had a 2 ml that you wanted to aliquot, and you are indeed getting the average around 2, but your standard deviation is about 0.06 ml, right. So basically you have a variation of 60 microliters in each of the aliquot that you ended up getting. And you are also able to remember the fact that the residuals that came for each of the measurements are above and below the average, which makes you happy. Let's take another example in a similar case, and in this case I have already done all the necessary math using the similar type of formula that we saw in the previous slide. So what you are able to see here, the experimentalist ended up measuring all these values again and determined what is the mass per aliquot that ended up coming, and converts it to the volume based on the density. After having done that, finds what is the difference between what aliquot has been added and what was expected to be added, and this has been done for each of the step, and you are able to realize the average volume difference comes up to minus 0.26. In the previous case you had something very close to 0, which indicated that you had a very reliable, basically a precise way of adding aliquots, but in this case you are able to realize that's quite far away. That indicates that your measurement is erroneous. And one important thing to remember is that in this case you had quite a number of values that go above and below the average. For instance, let's plot it again to take a look at it. You are able to realize that good number of values go above and below, so that makes you feel good. But on the other hand, in this case you are already able to observe the fact almost all of these values are negative. So why don't we plot and take a look what is happening. When you plot, what you are able to realize, all the deviations are below the 0 line. You want to be as close as possible to the 0 line, and you are able to realize all these points are below the 0 line. This clearly indicates that either one measurement completely offset all the other measurements, such that although it's randomized around this value, it's quite far away. It's randomized around the mean value of minus 0.25. However, you are trying to make sure the average goes to 0. So this clearly indicates you're shifted from wherever you're supposed to be. So this clearly indicates a systematic error that has come up in the researcher's analysis. Of course, repeating the analysis here, you end up getting a standard deviation that's very close. You got 0.1 earlier, you're getting same 0.1 here, but let's try to see what is the accuracy that comes up for this measurement. Once again, that we do by taking a difference between these values. And what you are able to realize here is that the researcher has had an initial measurement which was about 0.15 away, and there are some measurements that once again keep on repeating to a similar magnitude. So now let's quickly figure out what is the average. You are able to realize it's coming close to 1.97, 98 actually, and the standard deviation is about 0.1. Now if you see the similar analysis done for this researcher got 2 plus minus 2.00 rather 2.01 plus minus 0.06. In this case, this researcher gets 1.98 plus minus 0.1. So this once again indicates the second researcher has about twice the amount of error or lack of precision that comes in the measurement, however the average value works out. Let's quickly take yet another example. In this case, what ends up happening, this has been done wantedly where the average is quite far away. In this case you are able to see a certain number that comes, but in this case it is much farther away. This probably once again indicates something. Let us quickly take a look at how much far away is this researcher in each of the measurement. You are able to realize that this researcher has the same level of precision as the example 2, which gives 0.1. However, the average is clearly shifted away. You are expecting an average of 2 ml, but you are getting something like 2.13 ml. So in the previous case you got 1.98 plus minus 0.10, and in this case you are getting 2.13 plus minus 0.10 or 0.09. So although within 2 standard deviations these 2 measurements agree with each other, even within 1 standard deviation they are just barely close to each other, but definitely within 2 standard deviations they agree with each other, you are able to realize that in comparison to the first researcher who got 2 plus minus 0.06, these 2 people are less accurate and less precise. Accuracy cannot be told for the second guy, where the accuracy is still good but the precision is poor, but in this case you are able to realize that the accuracy is poor, so as the precision. So you would want to mimic the scenario as the first researcher by making sure your experimental setup is done in such a way that no systematic errors crop up. Okay, in this experiment what we saw so far is how to use a software, in this case a simple spreadsheet, in order to make an analysis and try to see whether you do get systematic errors. So what do we mean by systematic errors? When you are trying to measure 2 ml, in this case if you keep getting an average that is farther away, which is 2.13, there is probably some error that you are consistently making, and in this case if you are able to realize when you want to aliquot 2 ml, except for this measurement, all the other measurements are above the 2 ml. This once again indicates there is a systematic bias that comes into the data. On the other hand, if you are able to see the first researcher, when you wanted to measure 2 ml, you have values that are above and below 2 ml within a small error that comes up, an equal number of values above and below 2 ml, that helps you get a fairly accurate measurement as well. This is a simple example, but as you start doing bigger experiments, larger number of data sets come up, and you would have to do data analysis at every step, which ends up also propagating different errors that come up. If you remember, we learnt about what is error propagation, and those things also start coming up. In this case, where all you could have an error propagation is that the density measurement is assumed that it is correct until the 4th decimal. It could be a case where your thermometer wasn't good enough to give you within plus minus 1 Kelvin, or your density measurement is a little erroneous, or you ended up using water that had some contaminants, and at the same time the weighing balance that you end up using need not be calibrated, or it has a constant or a proportional error that ends up coming. Therefore, it is always a good idea to calibrate the instruments before you start, and each of the measurement that you end up getting, the actual volume is obtained from the density, so therefore the error gets propagated from there as well. And finally, what could end up happening is that researcher, as you are copy pasting, you might end up making some mistakes which result in erroneous measurements. Luckily, that is personal error, and that will end up giving a gross mistake from the measurement that you end up making. So you would be able to pick up what is a gross error. And on the other hand, systematic errors would come up if you are having all values above or below a certain value that you are trying to measure. Calibration errors have to be taken care before you start, and let us say that all of these have been taken care and you still end up getting a standard deviation of about 0.06. This indicates these are indeed random errors, and the only way for us to find this out is to repeat this measurement several number of times and see how much the standard deviation changes, and trying to get a histogram plot. Once you get the histogram, if you are able to get a nice normal distribution, that kind of indicates that this is indeed a random error, and you probably cannot reduce it any further due to whatever inherently exists in the system. So I hope this has given you an example of how to use software, and in this week you would be given data so as to analyze using simple spreadsheet software. And to start with, this is an example where it's a linear regression that we ended up fitting to understand how the data can be analyzed. And to finish up, same way we ended up doing a linear fit for the first one, you can do it for this one as well, just to see how far does the measurement deviate from the average value. You might still end up getting good fits here. You still end up getting an R square of 0.9999, which indicates it's a good fit, but unlike the first example where you had a value very close to 1, so you had something like 0.9919, in this case you are having 1.075, which means that it's about 8% off, meaning that for each of the measurement you are adding about 8% higher or lower, and the standard deviation in this case a negative of minus 0.05, which means that it could also have started with slight shift that ends up coming. So one is able to understand that the same analysis could be done in subtly different ways to have an idea how far is your measurement and how to be careful when you are making such measurements. In the next class, we will be trying to take a look at how to determine enthalpy of dissolution of a solid solute in water and use some similar software to get what is the enthalpy of dissolution. Thank you very much.